So our next session, as you know, is by Professor Norman Margolus on information mechanics, then and now. So I first want to thank Professor Margolus to accept our invitation in such a short notice. I just mailed him 1 week back, and although he has this time constraint and it's a very early morning in his time, but he agreed to interact with us and give his talk. Let me introduce him briefly. Professor Norman Margolus is a renowned physicist and computer scientist who is known for his fundamental work on cellular automata and reversible computing. He was a doctoral student of Edward Fredkin. On his memory, our webinar series is organized, and he received his Ph.D. in physics from MIT in 1987. He collaborated closely with many eminent scientists like Tom Toffoli, Charles Bennett, Gerard Vichniac. Within the MIT Information Mechanics group, he founded and was a chief scientist for Permabit, an information storage device company. During and after his PhD, he focused on creating and programming computers that preview and start using massively parallel applications in a cellular automata format on a microscopic scale. He co-authored the seminal book Cellular Automata Machines with Thomas Toffoli on physical modeling using cellular automata. His work includes influential papers on quantum computing, energy metrics in physical dynamics, reversible cellular automata, accumulating over 10,000 citations across his top 10 publications. Professor Margolus is currently focusing on theoretical questions at the interface between physics and computation, and exploring the foundations of quantum mechanics at the prestigious Computer Science and Artificial Intelligence Laboratory at the MIT. So I would like to welcome Professor Norman Margolus once again to give his talk, and we have a lot of questions for you. We are very enthusiastic to talk to you and interact with you. So over to you, sir.
All right. Can you hear me?
Yeah, sure.
Okay, good. Just wanted to make sure it's working. It's better to give a talk where people can actually hear what you're saying.
So very good morning to you.
Pardon me?
Very good morning to you.
Well, good afternoon to you guys.
Yeah.
And it's a pleasure to be giving a talk in your seminar series. So information mechanics was actually the name of our research group. And it was supposed to convey, by the way, you can see my slide? Oh, actually, I probably need to start a presentation, right?
No, we didn't start it.
Hang on. I shouldn't forget that either, right? All right. Do you see it now?
Yeah.
All right, good. Okay. So this cover slide is actually a picture from Atlantic Monthly from April 1988. It was an article about Edward Fredkin. This was on the cover. It was, and the title of the article was "Did the Universe Just Happen?" And I thought it was kind of appropriate to use for this talk, since it's in honor of Ed Fredkin. What I plan to talk about is how I got started with Fredkin in this business, which will lead to talking about reversible cellular automata and digital physics, which from my point of view is actually the best model of classical mechanics, which although people don't realize it, is actually perfectly discrete, which I'll talk about. And then I'm going to talk a bit about cellular automata machines. This is supposed to be a cellular automata machine, which let us have kind of a window into these reversible digital universes. And then at the end, I'll talk about what I think is the biggest challenge in this field, okay? So hang on, this should be advancing, good. So Ed Fredkin beginnings. So how it actually began is I was a graduate student at MIT, a new graduate student. I'd been there for about a year, I guess, and was pretty unhappy with taking all these exams on physics that I'd learned and forgotten as an undergraduate, and not really, what I really wanted to do was think about physics and computation. I'd been thinking about that for a long time as kind of more of a computer person than a physics person. And I saw this notice up on a bulletin board at MIT in the Center for Theoretical Physics about a course on digital physics. I didn't notice that the date was from a couple of years earlier. And it was talking about Ed Fredkin and this course, with all these ideas about deep connections between physics and computation. And so I ran off actually to where the course, I think it wasn't exactly this poster, because the poster I saw had the classroom and everything and time on it. So I ran off to join the class, and there was nobody there. And it was then that I realized that this was an old poster that, it had introduced me to Fredkin by, the accident that somebody had left it up for a couple of years, okay? And so I went there, and I was going to tell him all about, how I wanted to think about physics and computation and so on. Instead, he told me about that. The one thing that I hadn't thought about before was the whole idea of reversibility. That was something that was new to me, and it was obviously a deep and important idea. And in particular, the thing that most struck me was the billiard ball model, which I'm sure you're familiar with it, but I'll just show you. The idea is that if you start billiard balls with the right, size and a perfect, imaginary perfect world, right? You can have the balls at integer times always be at grid points, and the whole thing is reversible, right? And the important point, though, is that a billiard ball collision acts like a logic gate, because when the balls collide, they come out on different paths than they would have if they didn't collide. So the outer paths are only if you get a ball coming in at A and a ball at B. So it's an and function. And the other paths, this is like, if there's no A, you get a ball coming out at this point. And you get the ball B coming out at this point, and vice versa here. So a collision does logic. Now, Fredkin came up with this model actually in response to criticism from people like Carver Mead, who said that reversible computing was physically impossible, okay? And Fredkin was always coming up with these very simple, elegant examples of things. And this is really a beautiful example that, ordinary fundamental, classical mechanics perfectly supports, at least at a conceptual level, reversible computing. And this is also, this kind of model also acts as kind of a bridge between physics and computation, which, today, I think most physicists believe that that's an important connection. In those days, nobody believed that, okay? This was a radical idea. And in fact, this is Philip Morrison, a famous physicist at MIT. And some of his students went to Fredkin's class. And, he was telling them about, maybe this is how quantum mechanics really works, and, in among ideas about conservative logic and other things. And they asked Morrison what he thought of Fredkin's idea that, maybe the universe is a big computer. And Morrison was reported to have said that Fredkin is a computer person. So he thinks that the world is made out of computation. If he was a cheese merchant, he would think the world was a big cheese. All right. Now, this next picture, this is only a few weeks later, after I started with Ed. And I'm behind the camera in this picture, taking this picture on an island in the Caribbean where Ed is getting married and Richard Feynman is his best man, okay? And this was a somewhat surprising development. In fact, Ed forgot to mention to me there was going to be a wedding on this. He was taking me to the island, which he somehow owned. But he didn't mention that there was going to be a wedding, so I had to borrow some clothes to actually wear to the wedding. But this is when I began to suspect that Fredkin was not an ordinary person. I mean, he had no degrees, but he was a tenured professor at MIT and former head of the Lab for Computer Science. He didn't even have an undergraduate degree. He spent his time instead becoming a jet pilot in the US Air Force. He came from very humble beginnings. It was so poor that they sometimes had to move late at night to another apartment because they were so behind in their rent. But at this time, he owned an island in the Caribbean, basically because he started one of the first information companies and made a lot of money from that. And the thing I would say about, having seen the poster and met Ed and started to work with him, was that my life suddenly felt a lot like being a character in one of the science fiction stories that I liked so much. All right, so oops. One of the first things that happened, like a few months after I started, was that Ed Fredkin and Rolf Landauer and Tom Toffoli held a meeting on physics and computation. And Tom Toffoli, I don't know if he's here, he was going to try to watch this, but he did all the work. He was sort of the assistant, and Ed and Rolf were too senior to actually do the work to make the conference happen. And this was sort of similar to, in a way, to what Ed had done when he was head of Lab for Computer Science. And he'd started the field of time sharing of computers. Big computers in those days were expensive and they were shared. But it turned out that at the time, only about half of the people in the world thought that was a good idea. So he held a conference and he only invited the people who thought it was a good idea. And that started the field. So he did something similar with physics of computation. Hardly anybody thought that physics and computation were deeply connected, but he invited all these people, including a lot of prominent people like Wheeler and Feynman and Dyson and so on. And this really started not just the field of physics and computation, but quantum computation, largely because of a talk that Feynman gave, which, by the way, I transcribed as Fredkin's student. I got to do things like that. And in fact, I visited with Feynman for a year and had a lot of fun playing with him. And anyway, at the end of the talk, this is near the end of the talk, which started the field of quantum computing. His talk called Simulating Physics with Computers. And he says, the program that Fredkin is always pushing about trying to find a computer simulation of physics seems to me to be an excellent program to follow out. He and I have had wonderful, intense, and interminable arguments. And my argument is always that the real use of it would be with quantum mechanics. He always sort of criticized Ed because Ed just wanted to make classical models, and he thought that at some point, somehow, the quantum mechanics would follow, because it seemed so obvious to him that physics was just an ordinary, cellular automaton. I'm going to sort of comment on this. I think, well, let me comment on this later. but my views on this are somewhat different than Ed's were. But I think it was a very worthwhile endeavor anyway. Okay. And just, this is Tom Toffoli. This is what on the left there. This is a view from one of the beaches on Ed's Island. I figured that while I was at it, I needed to show you that this was a really nice place. And we used to have meetings on the island, not just the people in our group. There's Tom and Ed, and Richard is his son here, his new son. We used to have meetings on the island, which, what we would do is there'd be a few, famous researchers like, Kadanoff and Kreutz and, whoever, we wanted. And, we wanted to talk to them about physics and computation. So we would invite them to Ed's Island on the Caribbean. And for some reason they would come, and in between, the windsurfing and the pina coladas, we could ask them questions about deep physics. And just the last picture here, this is from last June at Ed's funeral. And he was buried with full Air Force military honors because he was, after all, an Air Force fighter pilot. And, at a certain point, the jet planes flew overhead. It was really very nice. Anyway, I want to now talk a little bit about one of the main things I worked on with Ed, which was reversible cellular automata, and why that was an interesting thing to study, and how you make reversible cellular automata, okay? So one of the reasons, well, the main reason that cellular automata, I think, are interesting for physics is that we live in a world with finite resolution. Here's a cartoon from Reuben Bowling. Good Lord, what a discovery. What is it, Dr. Professor? Use this microscope to view the corner of this table. Pixels, everything is made up of them, even us. Well, this is, it's not literally true about our world, but it's, essentially true. In fact, these people, the guys who started off quantum mechanics, they realized that a finite physical system had only a finite number of distinct states it could be in. This is starting with Planck and the entropy of a black body radiation and so on. And before that, Boltzmann had he'd assumed sort of an arbitrary grain size for physics. What's the smallest piece, of position momentum space or whatever, in counting states, and nothing, and it was arbitrary. But suddenly, with the advent of quantum mechanics, it was actually entropy was an absolute count of distinct states. And so, knowing this, as a physicist, I knew this, okay, and even before I was a physicist, I knew there was some sort of discreteness, and so I had thought, oh, that must mean that the world is something like, the game of life, right? Because it's computation universal. If you try really hard, you can make some structure here. That's a glider gun, and you can make computation happen. But first of all, computation is a very delicate thing and easily broken here. It doesn't happen sort of as a natural, spontaneous thing. And the other property is that if you just start from a generic initial state, you're just a random pattern. And we watch for a bit. This is running at, I think, several hundred frames per second. Look, it's done. That's the end of it. Okay, and there's no macroscopic stuff happening on. So life is short. And if we look, if we look close, you see it's actually still wiggling a little bit, but really, nothing interesting is happening anymore. So that's the motivation behind reversible systems, because reversible systems can't get stuck. You always have to be able to go backwards. And if you have a small area that's doing something, eventually it runs out of states and it has to do something else, right? It can't get stuck. And in fact, reversible systems on average have a cycle time that's about half of as long as the maximum. So if you have n bits, it's a cycle time of like 2 to the n over 2, very long. And so you get a much more interesting universe with a reversible rule, because it just goes on a long, long time. That's one of the properties of interesting universes. So the first technique that we thought of to make reversible cellular automata was based on an idea of Fredkin and Guy Steele about having second-order systems. So what I mean by that is we're going to do a two-dimensional cellular automaton. We imagine that the state has 2 layers, and that when we update it, we could think of them as like past and present or something, right? It's second order, like physics is second order, most of the equations. That you could look at, say, the past and change the present into the future. You look at the black layer, change the white layer, then look at the white layer and change the black layer. And because you don't change the layer you're looking at, if I make some change, like say, flip one of the bits here, right? I still have the information that caused me to flip it, and so I can always do the operation again and unflip it. So there's always enough information to go backwards in these second order systems like this. And the very first rule that we tried to look at on a computer was reversible or. We look, if any of these bits are 1, we flip this guy, and then going the other way. And you run a step and not much happens, except that on our computer, a couple of minutes are gone by, right? And in fact, we captured images all night, and got something like that, except on a much lower resolution and so on than I'm actually showing it here. And that's when we realized we needed some special hardware, some cellular automata machines, in order to be able, to see live TV from these imaginary worlds, right? And so Tom built our first CA machine. Whoops. I'm not using the pause buttons in my presentation software properly. And we saw things like this, right? We're always wondering, well, what can it do next? Nobody's ever seen these reversible systems. We were the first ones to look at a nonlinear reversible cellular automata, and it was quite interesting. And this is more or less what we saw when we ran this on our first CA machines. Now, another technique to make reversible CA is to basically do the same thing, but as a checkerboard. So in a checkerboard, we can, at even times, look at the black guys and change the white guys. And then at the odd times, we look at the white guys and change the black guys. And again, we're not changing any of the guys we're looking at. So if we flip a bit here, we still have the information after we've done it to flip it back. So it's perfectly reversible, okay? And so one interesting simple rule is an Ising rule. Ising models think of the bits as spins which have a bond energy between them. Say +1 bond energy if they're the same, if 2 1s are next to each other, and say -1 bond energy if they have opposite values. So if you flip the middle, when 2 of your neighbors are 1 and 2 of your neighbors are 0, after the flip, you've still got two of your neighbors 1 and 2 of your neighbors 0. So the number of bonds with each energy has not changed. So that conserves a bond energy. And Michael Kreutz used that idea to make deterministic Ising models. This one's without a heat bath. You have to start. We started with 25% ones here. If we started with 50% ones, nothing would happen because it's reversible, and the maximally random state under a reversible dynamics wouldn't be able to change. So this is actually a model of magnetism. But it turns out if we take that exact same dynamics and start it with this kind of a wavy boundary and hold it fixed at the edges, but exactly the same dynamics, this is what it looks like. So, the kind of physical wiggly things you saw in that evolution, this is actually a perfect harmonic wave. It's exactly obeying the wave equation along that boundary. And if you think about it, you realize why it's obvious that it does it. But it just shows how easy it is to get fundamental equations of physics out of very, very simple reversible rules, okay? And Charlie Bennett, actually, in a challenge from Wolfram, this is the way Bennett tells the story, that Wolfram apparently had told him that there are no interesting reversible rules. And so in 1D maybe, I guess, because that's all that Wolfram was looking at. And so Bennett made up a rule exactly like the kind we were talking about earlier with 2 layers. And he used a neighborhood like this: 1 neighbor in one layer and 4 in the other. So it's just like the Ising rule, or the Ising dynamics, that if 2 of the neighbors are 1, he's going to flip this guy, and there'll be a bond energy that's conserved. And then he does it, in changing the roles of the 2 layers. So this is, second order in time. And if we start with a little patch of randomness at the top, the dynamics looks like this, okay? And we get all sorts of, structures, little particles moving at different speeds and wiggling around and doing all sorts of things. So in fact, there was an interesting reversible one-dimensional cellular automata. I don't know, Wolfram may remember this story differently, but that's the way that Charlie Bennett told it to me, okay. So you can also make 3D models with this Ising conservation. And this is a 512 by 512 by 64 system. It's an Ising model, but with a heat bath. So you have some extra variables that just, they hold a number which you take as the energy, and you can make transitions as long as there's enough room in the heat bath to put excess energy into, or enough energy in heat bath to, as long as the transition conserves the energy, including the heat bath, you make it. And that lets you also cool the system by removing energy from the heat bath, and then the rest of the system gradually sort of solidifies here, anneals, I guess. And this was a simulation on Chem 8 done. The light and rendering is also done as part of the simulation. And another reversible model using this kind of structure was something I did with my student Raisa de Souza, which is a model of reversible aggregation. It's like a diffusion limited aggregation model, but reversible and with a heat bath. And in this case, you're not removing heat from the heat bath. You just start with an empty heat bath and you come into equilibrium with it. So you can see that the dendritic structures are sort of annealing. They come and they go and they grow in some sort of smoother way, right? Now, the most interesting models, though, most interesting reversible models are lattice gases. here's an example of a lattice gas. This is the classical lattice gas of Hardy, de Pizzi, and Poumon. The idea is you imagine particles starting off on the lattice. It's sort of like the billiard ball model, but they, when they collide, they come out at right angles. And it's, of course, reversible. And that simple collision conserves particles, conserves momentum. All right. And so it's very easy to get a lattice gas that's reversible and has conservations. And that simple lattice gas, if you just run it from a random pattern, completely random pattern with a hole in the middle, okay, you get a sound wave, which is round. And in fact, we weren't aware of the work of Hardy, de Pizzi, and Poumon, but we've been playing with this kind of thing, and we showed this to various people, including Poumon and including Wolfram, and they got excited about this because suddenly it seemed real that you could do some sort of hydrodynamics with lattice gases. This very simplified molecular dynamics with only a few directions, and digital particles. Of course, this runs backwards. Everything runs backwards. It's more impressive, though, if I run it backwards on a cellular automata machine. So I'm actually running it backwards. As far as you're concerned, I'm just running the movie backwards, right? But we're actually running the simulation backwards. And exactly the same dynamics, if you just color the particles, but the color has nothing to do with the dynamics. It's just, so we can see what happens to the individual particles under the dynamics. You see that you get both the sound wave, and of course you get diffusion of the particles. So both phenomena are actually happening at the same time in the same model. And this seems, since you could start these reversible models with any pattern you want, it seems a bit starker than that all of physics is reversible, right? But the idea that you could make some little drawing and start the universe from that, and then run backwards and get exactly that drawing is actually kind of funny. This is a cartoon by Sidney Harris. If we take our current model of the universe, so you got the physicists in here, you may not see them. If we take our current model of the universe and run it backwards 13 billion years, we get something resembling Donald Duck. There must be something wrong here, he says. All right, maybe we get Donald Duck. All right, here's one of the first models I made once I saw that we could have sound waves. I thought, well, if you can have sound waves, we could, just have sort of ordinary, 4-direction lattice gas out here, but we can draw an area here where we're going to change the dynamics, and half of the time we'll do nothing, and half of the time we'll just do the same dynamics as everywhere else. So that should give us sound waves that are half as fast in here, which means we should have an index of refraction, right? So we'll let this is actually a solitary wave. It's more dense than an ordinary wave. It stays together better than an ordinary wave. If we let that run and hit the area of slowdown, what you get is nice refraction and reflection. You got waves both ways, and that seems kind of nice. It's very easy, and you could imagine making models of all sorts of things that way. In fact, gravity is one of the characteristics of gravity is it slows down the dynamics, right? the greater the gravitation. So you could imagine making some simple model of gravity just by having some density which slows down the dynamics. Anyway, it's sort of intriguing. Another kind of thing we did, actually, British Hatzlacher and Pomoe came up with a more sophisticated model with 6 directions. Turned out that 4 directions didn't give you full macroscopic rotational symmetry. It was slightly too simple a model. It had too many conservations. But with 6 directions, you do get real hydrodynamics. And here, this is a 6-direction lattice gas with, we've thrown in some extra tracer particles that follow the flow, just so you can see more clearly what's going on. And there's an obstacle here, and the particles are introduced at this side going this way, and they're sort of swallowed up here and turned back into a uniform flow. So if we run that, you actually get von Karman streets and all these normal things that you get in hydrodynamics. And this is just a 6-direction lattice gas, very simple model. And that became a whole industry that stemmed from that. I should say that our friend Brazel Haslacher, when he was one of the people who worked on this stuff and announced it and so on. And in some article in the Washington Post, he was saying that this is going to put all of hydrodynamicists out of business. So he immediately made friends with the whole community. He was trying to convince that this was interesting. Now, one thing that's wrong, or one thing that's an issue with the billiard ball model, if you want to turn it into a cellular automaton, is that the collision goes like this. The middle of this particle does that, and the middle of this particle does that. And so if you try to shrink the particles to a point, there's this non-local interaction here. And that makes it a little bit difficult to turn it into a cellular automaton in a straightforward way, because cellular automata are supposed to be completely local. In fact, if you imagined a whole bunch of particles, a bunch of them coming down this way and a bunch of them coming up this way, you'd have a whole stack of these guys, and how far does the interaction go and so on. It's, I did, as one of my first projects, I found several ways of making a cellular automaton out of it. The best one I found at the time involved breaking the rules so that you had these block partitions, that you updated blocks, say the red squares first and then the white squares alternating. And you could get something where pairs of particles, their distance between them represented the size of the balls. But this has a defect that when the particles are colliding, I don't know if you can see me, when the particles are colliding, they do a little sort of dance that sort of represents communicating the information across the width of a ball. And so there's actually a delay in every collision. And so the center of mass of the system is not conserved because the center of mass should move at a constant speed, for the freely colliding particles. Anyway, but it was interesting to think about partitioning and making simple models and so on. And later on, years later, I came up with what I consider to be a much better model, cellular automaton model of the billiard ball model of computation. And I did that by changing the model. You always have to cheat somehow if you want to have a good result, I think. So in this case, we start off with these balls look the same. But when they collide, we have them squish inward and then come out. And that's perfectly reversible. These are just elastically colliding balls. They squish a lot, and so they take a while before they come apart. And this actually has the same logic as the billiard ball model, because the balls, instead of being deflected outward, they're deflected inward. And so we get A and B coming out on different paths than A or B alone. And this has the advantage, if we look at sort of the whole time history here of what happened, the interaction sort of happened here. They came together, the balls stuck together for a while, and then they came apart. You could reduce the size of the balls to 0, and this would still work fine. An interaction where stuff sticks together for a while, but the interaction takes some amount of time and then stuff comes out again. That's perfectly reasonable in physics, and works very well, for instance, with relativity. The billiard ball model, the original billiard ball model, was not as good a relativistic model. This is exactly a lattice gas. You don't have to do anything to turn it. It's a lattice gas. You don't have to do anything to find the cellular automaton version. It is a cellular automaton. Okay, so that was actually quite useful. And so I'd like to use that model to give you sort of a take on digital physics, or my version of digital physics, which is the classical mechanics is digital, okay? And I'll use this model as an example. So this is our classical mechanical computation, right? The balls come in, they swish, and they come out again, right? In quantum mechanics, there's a whole field of quantum computation. And there you have like unitary gates. You can have sort of ordinary classical gates that are just doing a classical reversible computation. Like this is an XOR. This value is being XORed into this line here. If you had two things here XORed in, that's the AND XORed in. That's the Toffoli gate, the famous Toffoli gate. So you have classical gates. Well, one way of looking at it is you have classical gates plus some operation on a single quantum bit, which rotates it and turns it into a superposition or a different superposition of 1 and 0. That's quantum computation. This is a model of classical computation. If you just leave out this one, you only have the classical gates, and so your quantum computer can do a classical computation. So we can imagine classical mechanics being done by a quantum system. And this is sort of, you can think of this model of classical mechanics as having an inherent level of discreteness, that we want this position to be distinct from this position. We don't need more than that. This position distinct from that, and so on. And in fact, ordinary classical mechanics is infinitely distinct, but quantum mechanics says that in fact, you can't have infinite distinctness. With finite energy and finite momentum, things change at a finite rate in time and in space. And there's a thing that looks like an uncertainty relation you get from quantum mechanics, which I discuss in a new paper here. This is sort of a generalization of the idea of a relation like this between energy and time, momentum, and the distance between distinct positions in space has an uncertainty relation that looks like this. This is the magnitude of momentum. This is the distance between distinct positions in space. So in a model like this, if these are actually the minimum distinct positions, you're imagining a classical mechanical system which has sort of minimal distinctness. You're thinking of your lattice gas as being a model of all that's going on. There's no distinct state in between this being here and this being here, right? So that's the minimum distance. That's the distance it has to go to have a distinct transition. And in this collision, in this part here, when it's moving horizontally, that's the distance, which is shorter between distinct positions. in fact, it's perfectly consistent to think of classical mechanics as being maximally distinct. That is, that at the most microscopic level, classical mechanics, it's actually a quantum dynamics underneath. It has to obey quantum mechanics with finite energy and momentum. It can't have infinite distinctness. So at most, it can be maximally distinct. And if we imagine that, then we can actually assign an intrinsic energy and momentum to a lattice gas. And this is sort of a fundamental physical model. It's the least energetic, least momentum model you could have. I'm only using the momentum relation here. And we also get velocity there's a characteristic time for your lattice gas between updates. And so from the time and the distance, you get a velocity and a momentum. And from relativity, if you have a velocity and a momentum, you know what the energy is. I'm not trying to get the energy directly from the rate of change in time, because if this is the full relativistic energy, it should include all the changes that are happening inside of these things also. So I can't get it directly from a relation like this, but I can just get it because I know momentum and velocity. That tells me the energy. And in fact, this relation here, if you're not so familiar with relativity, but you remember E equals mc squared, if E is mc squared, this is just m equals p over v, which is just p equals mv. This is just the definition of momentum, okay? So, so this is interesting because we've given, I guess I forgot to mention the h here. The h over 2 disappeared because I'm a physicist and we like to use units in which extra factors like this disappear. So if h equals 2, this is just 1, and so then p is 1 over lambda. Sorry about that. I should have mentioned that. And then here we'll do the same thing. We like to simplify this, so we'll let our speed of light be our unit velocity. So all velocities are less than 1, and then that's simpler also. And then so these simple equations tell you the intrinsic energy and momentum in a classical mechanical lattice gas. So if you're playing with these kind of reversible classical mechanical lattice gases, you can enjoy the fact that you're also being a theoretical physicist. Okay, these are fundamental physical models, and you can understand all sorts of things about relativity and least action and so on by thinking about these models. And you get things like least action principles and so on for cellular automata, because these models are exactly equivalent to classical mechanical models that have those properties. Okay, but going the other way, the classical mechanics gets these discrete properties. They're just counting stuff. Okay, it's counting is just as important in classical mechanics as in thermodynamics. All right, so cellular automata machines. I'm actually doing okay. I might actually finish in an hour. This was very important to make cellular automata machines so that we could actually watch and play with these models. Ordinary computers are just too slow, and it was miserable trying to wait for things to. This is a long time ago, but our ambitions are infinite and our resources are finite, and so things are always way too slow, right? So the first cellular automata machines, were built by Tom, and the idea was, this is supposed to be a memory that, we show its contents on the screen by just scanning it, raster scan. In those days, you had monitors, that were like TV monitors where it drew the image, just scanning across like this. And if you had your memory scanned at the same time, you'd see an image on the screen. And so what we did in the CAM machines, what Tom did, you kept a few lines here in a buffer as you were scanning, so you could expose a little neighborhood around whatever point, is in the sort of the middle of your scan. And you send those bits of the neighborhood, whoops, I pushed too hard. You send those bits of the neighborhood to, a little circuit here or a little lookup table. And the result you put back in the center cell, wherever it is you're scanning. And you do that over and over again. And that's your cellular automata machine. And it runs, at the rate of TV. And that was fun. I actually, on the first machines, this was a little breadboard. And so you put together a few OR gates and an AND gate and an XOR gate or something. And you never had so much joy putting together a little bit of digital hardware as, the beautiful pictures you would get, right? The later cellular automata machines, this became very serious because we discovered that you could do hydrodynamics with cellular automata. And so, we should make serious machines that can do big systems and so on. So CAM8 was a lattice gas machine, not just because, lattice gases are important for hydrodynamics, but because lattice gases are actually a very general model of things like cellular automata. You can make everything out of a lattice gas. So let me explain sort of the conceptual structure of the thing. That you have, here we have what's supposed to represent a plane of bits. If you think about an ordinary, well, think about this in 2D to start with, right? In 2D on your computer screen, you have pixels, and the pixels, they have some order, and you could think of all the, highest order pixels on your screen as a plane of bits, and the next order ones as another plane of bits. And if you could shift the planes relative to each other, then and then scan the whole thing in some order, that would control which pile of bits, which pixel gets accessed at the same time. It would bring together a neighborhood of bits, which you then put through a lookup table and put back. And so CAM8 is like that. Instead of having neighborhoods, we just had shifting bit planes. So you can shift things as much as you like, and you had any neighborhood. If you just have to work at it a bit. If you have more neighbors than bit planes, you'll have to take several steps. That let us do, if these are hyperplanes, then these piles of bits are in more dimensions. And then, of course, what you do is you have modules like that arrayed in 3D, and they communicate with each other. So if you have this module here, and you're shifting a bit plane this way, some of the bits go here and some of the bits go here through the wires connecting them. And meanwhile, from the guy on the other side, some bits come in here because everything's being shifted the same way. So you can, once you make a chunk of a space, you can make the space as big as you like by putting together modules. And that was the architecture. We only made relatively small machines because at a certain point, our funding agent decided to cancel all parallel computing projects because everybody knew that parallel computers should just be piles of Intel chips. And that was the end of the project for them. Our collaborators were not very happy that there was no more work going to be done on those machines. They were doing all sorts of interesting things. There was another project. Brazel convinced me to design a much faster version of this. You could put logic on a DRAM chip, and that would run very fast because on a relatively small DRAM chip. On chip, you would have at that time like a terabit per second of access to the memory. And these are just processors that take things out of one memory, run it through a lookup table, and put it back into another memory. And so with a little bit of tricks, you could actually you make chips that would be able to do something that's similar to CAM8, but even better, that would use the full memory bandwidth of the memory on the chip. At that time, it was 1 terabit per second. Currently, people are using logic and memory on the same chips in AI applications for things that get like 100 terabits per second. So you could get 100 terabits per second of actual useful updates, and then have thousands or even hundreds of thousands of such chips. And so the scale of things that are possible for this kind of bitmap virtual reality is really staggering and hard to even play with any sort of computer that isn't a cellular automata machine. Ed Fredkin always thought we were sort of dumb for making hardware, because everybody who made hardware, eventually there's the exponential speed up, exponential progress of memories and processors and so on, and you get beat out. But I don't think that's true for this, because we make that, first of all, it's such a big speed up, and secondly, we get that same exponential speed up for our next thing also. Anyway, I actually, that same kind of shifting of bit planes works extremely well as an architecture for a software simulator. So you could play with this sort of at not, at tiny rates compared to real hardware, but at very good rates compared to other ways of doing it. So a program similar to this is all it would take to do like the 4-direction lattice gas. And I should say that we did some things on our cellular automata machines that were not, just ordinary physics simulations. You could see that we were obsessed with physics simulations. But you could do very good logic simulations. Now, of course, the obvious way to do a logic simulation is you make a CA rule that lets you have spots that are wires and spots that are, this kind of logic gate, and spots that are that kind of logic gate. You just mark the spots using some of the bits in your cell, and then some of the bits are the signals. And so you get you can see the signals moving through the wires and doing some sort of logic, right? Let me see if I press the right button here. Stop that. The one on the right here is actually a different way of doing it, which takes advantage of the fact that we have virtual processors. So look here, you can see that you don't see signals moving in wires, you see entire wires lighting up. And that's because in this simulation, what we did was, here I can pause this. Oh, come on. Maybe I can't pause it. All right, I'll just leave it running. My ability to control things with 2 movies on the same slide apparently is not great. The idea is, this is actually a design of a microprocessor. And what we do is in one clock cycle, all the things that happen at the beginning of the clock cycle, we put at this end, all the gates, we lay at this end. All the gates that happen at the end, we put at this, that get, activated near the end, we put at this end. And we just sort the whole circuit so things happen in order, left to right. And this is one clock cycle. And then, since we have virtual processors, we can have the whole machine working on this slice and carrying the result with it a little over to this way and working on this slice and so on. And so in the time it takes to update all the cells once, it's then a complete clock cycle. Instead of over here, you had to wait for the signals, it took a step, an update of the whole space for the signals to advance each little bit here, right? And get to a certain place. So this ends up being thousands of times faster. And it's something that the cellular automata machine can do perfectly well, since it's, you get from the fact that it's virtual, you get to have as many bits as you like in a cell, you get to have the space shaped however you want, and you actually get to do things like, we do the same thing when we do the 3D rendering that you saw for the the light in the Ising simulation. Instead of it taking, light crawling through the space and reflected back in one sweep of the space, the light gets all the way through and touches everything, and in another sweep of the space, the other direction, you get all the light back. And so, again, thousands of times faster. And there's, all sorts of things that you can do like that, that are enabled by that. And in fact, this kind of machine would be very good for doing very large, not just logic circuits, but things like neural nets. So, we almost built the space RAM thing like 3 times or something, but various things diverted us. It would have been probably a very good thing to have right now. Another non-physics, well, less physics kind of application was image processing. We did some stuff with like MRI images, MRI 3D data, bitmap data. And this is an idea that Tom Toffoli had about how to do rotations by shears. Since you can slide bit planes, shears are a very easy thing to do. And with 3 shears, you can do a rotation, an arbitrary rotation, but it sends each bit somewhere, so you don't lose any information. It's a perfectly invertible operation, and you can keep rotating things as long as you like, and you get back exactly what you started with when you get back to the initial position. So that's pretty cool. Last thing I would say, just the big challenge is in reversible, well, the big challenge in the field, reversible CAs and physical computation, I would say, is to make models that are more like physics. So in fact, here's the critters rule on the big space. I think it's 2000 by 2000. I mean, big for the time. We could run this at, at hundreds of frames a second on our CAM8. But you don't see, macroscopically, not much is happening. This is just becoming a bigger blob, right? It's not that interesting. And if we zoom in, you can see that, for instance, watch this guy here. That's the smallest moving object in the model, and he hits over here and then bounces off. The objects are very robust. You don't get stuck. When you have a bunch of stuff in one place, isolated from other things, eventually, if it's made out of 2 of the smallest objects and it's isolated, nothing else is hitting it for a while, eventually the 2 things have to come out again because you run out of states locally. So the objects are robust, the dynamics it lasts a long time. And you can have conservations and everything, but we still just got a blob. And we'd really like something more like this. Here's a model due to Jeff Yepes. These things are like hundreds of particles each. There's an attraction and a repulsion and an attraction at different distances. And you can see it looks quite physical. And that's what you really want to have an interesting, this particular model is irreversible, but as you saw earlier with like the reversible aggregation, with a heat bath or something like a heat bath, you can make these models reversible. what you really want for an interesting CA universe is much more than just computation universality. If you don't have computation universality microscopically, you're not going to have it macroscopically. So you're not going to have anything very interesting happening in the world. But that's just the start. As we noticed, having reversibility helps a lot also because it makes the thing last a long time and it gives you a realistic thermodynamics because you can't just erase entropy. The entropy increases and the coarse grain entropy increases. But you also want to have a macroscopic world. You don't want to just have microscopic stuff going on. And you'd like to have, if you have some macroscopic object that does something interesting, you'd also like to have a moving version of that object. You'd like to be able to put it in motion so that you can have, interesting things in the universe that move around and interact on a macroscopic scale. And for that, you actually need something like relativity, because relativity, special relativity, is just the idea that you have the same physics in different states of motion. So that your big moving object, your big object that's doing some complicated thing, it has a brain, right? When it starts to move, the chemistry doesn't stop working. So that's kind of the challenge, is to be able to have interesting macroscopic stuff, so we can, to see if we can have a world as interesting as ours with cellular automata. Let's see. Oh, yes. I was going to end, miraculously, I'm ending at approximately the right time. I can't understand how this happened. I thought for sure it was going to take too long. So I was going to show you a favorite cartoon from Larson to end with here. My God, Nathu, they're like nothing I've ever seen. They're looking at these cactuses, they're Eskimos. And I thought, this made me sort of think of Ed Fredkin's view of physics. Okay, these would be the physicists, and these are the wave functions. And my God, they're like nothing we've ever seen, right? And I kind of have, I guess, what I'm saying is that his view is that these things, that what's going on in quantum mechanics is like something you've seen, maybe. And what I would say is, my view is that I've spent like the last couple of decades or so trying to see how these things are, not so strange after all. For instance, seeing that classical mechanics is really, if you put in some constraints from quantum mechanics, it's really discrete and digital. And, in a sense, I think it's more like what the digital physics Fredkin was thinking about is than, the quantum mechanics is. Anyway, that's kind of my viewpoint. I am about to put a paper about this on the archive, in the next week or so. So if you want to read more about that, you can do so. And so I thank you for your attention. And we actually have time for questions, I believe.
Yeah. Thank you so much for the wonderful talk. I believe many of our participants have questions. I definitely have a lot of questions, but I'll first let the others ask. So the forum is now open for questions. Anyone can ask. Yeah. Deepak sir raised hand. Professor Deepak Thor. Sir,
Okay,
I'll request you to first introduce yourself a
do I have
little
to do
bit.
anything?
No, sir, you don't have to do.
Yeah, my name is Deepak Dhar. I wanted to ask you just this question. You said the velocity is distance lambda by tau, but
Yes,
in a cellular automaton, these can only take discrete values, or
that's
plus
right.
minus 1. So, but that doesn't look like classical mechanics much.
Well, no, sorry. Let me go back. Now I have a way to go back to these things. Let's see, oh, yes. Okay. Hang on.
Yeah.
Okay. So,
Yeah, this equation.
okay.
Equal
So
to lambda.
lambda is the distance between remember that what we're doing when we turn a classical mechanical system into a lattice gas is we're considering a very constrained initial state, but it still conserves momentum, conserves energy, it obeys the Lagrangian dynamics and all that. It's just a constraint on the initial state. There's no constraint on the dynamics, right? So when you make the particular model, there'll be some distance. This is the diagonal distance between the lattice points where you're only starting balls at those points, right?
Yeah.
Tau is the separation. Maybe I didn't say tau is the separation in time. Well, yeah, I think I did. Between the updates of the state, right? It's how long it takes a ball to get from here to here. It's also the time it takes a ball to get from here to here, because everything is back on the lattice after a time tau, right? Okay, and so this distance divided by this time is the velocity of this ball. This distance divided by this time is the velocity of this ball, right?
Yep.
Okay, and the fact that you've constrained the initial conditions means there's only a finite number of velocities. There's 4 velocities like this, right? And 1 speed like that, and there's 4 velocities like this.
Yes.
And that's it. Those are all the velocities in your model. However, if we change the lattice spacing or we change the time separation, and we can have the same model with any lattice spacing or any time separation, then we can't choose lambda over tau to be more than the speed of light, right? But other than that, we could have any space separation and any time separation, and that corresponds to a classical mechanical system.
No,
I mean, is that answering your question at all, or do you still have a question?
No, my question was that if you want to simulate a particular system, in that system, the different particles can only have finite number of velocities, then it doesn't give you enough choice, no? Or does it?
Well, it's a discrete, you can think of it as like discrete molecular dynamics. You could, when you saw the simulation of the hydrodynamic flow, that was a system that had only 6 possible velocities, 6 directions, 1 speed in each direction, okay? But it had enough symmetry that at a macroscopic scale, you regained complete rotational symmetry. What I would say, this is not, there's 2 different things here. I understand, I think, better your question, that this is always true, okay? That there's a discreteness to, to all of physics, including classical mechanics. This is a particular model that's enabled, since there's a discreteness, you can make discrete models, but the discreteness in classical mechanics is actually of a different sort. It's a continuous. I didn't get into this in the talk, but the way you get the discreteness it's very similar to what happens with bandwidth limited signals. In quantum mechanics, everything is waves. The momentum is waves, the energy is waves, and so on. And they're really classical waves. They're being used to describe something quantum, but they're just waves, okay? And if you had a finite range of frequencies, a finite range of energies, then you get finite distinctness. There's a limited time, between one value you can choose arbitrarily and another, okay?
Yes.
And so the discreteness you get from quantum mechanics is actually the kind of discreteness you would get from sampling. That the discrete samples are enough to give you the complete state, all right? But the samples could be taken at any angle, right? So you don't lose the rotational symmetry or anything. It's just that with finite energy and finite momentum, with enough samples, you've got all the information, and more samples doesn't give you any more. And so you get a discreteness of that sort. And here I'm just exploiting that discreteness in order to make models which, don't, the individual model here doesn't have the full character of classical mechanics, but it is a legitimate classical mechanical model that does have energy and momentum that are intrinsically defined by the level of distinctness. You only can have distinct states, this so close together in space or time, and that makes the classical mechanics itself discrete, but in a way that has continuous symmetries. And in order to make cellular automata models, we throw away the continuous symmetry, but we still have a connection to quantum mechanics. I mean, sorry, I didn't understand your question earlier, but I think maybe that answers.
Yeah. Thank you.
Okay.
Okay, so next question. Anyone wants to ask? Yeah, Supriti. Supriti, please introduce yourself and then ask your question.
Yes. Hello, Dr. Norman. I'm Supriti.
You are very
Your talk was really so much interesting, and I was just continuously looking at your slides and your work and your talk. So I have seen that you worked on second order cellular automata. In one slide you have mentioned. Actually, so from 2 to 3 months back, I've started, not 2 to 3, it will be for 6 months. I am working on that second order cellular automata, that is a reversible CA, and I am trying to find out the dynamics of this second order cellular automata. So,
Yeah.
and for that, what I was doing, actually, this work is with Professor Enrico Formanti, and what we were doing is that we were taking a special type of cellular automata where the state of cell I at time t is added to the states of cell I minus 1, I and I plus 1 at time t plus 1 to get the result at time t plus 2. So, and in this way, we were trying to classify the cellular automata by observing the dynamics of them and classify them into 4 classes like simple CA or periodic CA or chaotic or complex CA. So, sir, I want your suggestion about how I can proceed further to explore some more type of second order cellular automata, or so that I can study the major number of such second order Cs.
So there's, it's funny because the normal questions I get about cellular automata, I've been working on quantum mechanics lately, so these are the questions I used to get about cellular automata are, is there any other cellular automata that's interesting except for the game of life? Okay. And that's sort of like the question, is there any differential equation that's interesting except for the diffusion equation or something? I don't know. There's an almost infinite variety of things you can try. From a physics standpoint, my big thing was trying to make contact with physics. I think that even if you're not that interested in physics, making contact with physics means that you're making contact with a system that is interesting. You know that physics is interesting if you do some of the things, like have a conservation law, things like this. That gives rise to all sorts of interesting properties. Mm-hmm. For instance, the lattice gas that was giving the hydrodynamic flow, there's sort of a general principle in physics that if you have conservation of momentum, conservation of particles, and not, and you don't have a bunch of extra conservations in addition, mm-hmm. right? That you'll get hydrodynamics, so, there's a few principles just like that mean you're going to get interesting behavior, interesting macroscopic behavior, and all of that. So I would say, conservations and reversibility are really sort of the strongest properties in physics, and those are very easy to put in. Those are easier to put into lattice gases, or things like a checkerboard. Well, a checkerboard updating. But you basically, I think it's easiest to put conservations and reversibility into lattice gases because, a lattice gas, even like the 4-direction lattice gas we were describing, they come in here and they go out here. They don't interact with anything as they're moving between the lattice sites. All the interactions are at the lattice sites. And so we normally think of a lattice gas as 2 steps. You move all the particles, then you update what lands at the lattice site, and then you do it again. Since all the interaction, it's one site being updated only as a function of itself.
Yes.
Whatever conservations, reversibility, anything you want to put in, you can put in. And so that's actually a very good model for being able to make interesting things. You can also pile up as many bits as you like. So if you want to, like in the, when I had the reflection and refraction, just add a few bits and you have an area that things are moving slower in. You want to have flow past some object, you just draw the object using a few extra bits and so on. So it's kind of a very practical thing. Lattice gases rather than second order cellular automata. You can do what I would say, you saw that in the case of things like those Ising models, those really were second order cellular automata, but you simplify the situation by not changing, by looking at some part of the system and not changing it, so that whatever change you make elsewhere, as long as it's a reversible change, you'll be able to undo it. So you get a reversible model. So something, the checkerboard updating is second order, but it's a form of partitioning. The lattice gases are just sort of the extreme form of partitioning. You can play with whichever things you like, and you can have conservation laws and so on. I think that they're easiest to have in lattice gases. So that's, it's sort of my answer to your question, how to have more interesting second order cellular automata. Well, lattice gas is a second order. They're not exactly what you're thinking of, but I think they're the easiest thing to work with if you want to, put in interesting properties.
Yeah, okay. Thank you so much, sir. I'll definitely look into that part of the lattice gas to more explore this second order CE.
Okay, there's also a paper that I flashed past at some point here. Let's see, where would it have been? It's probably was it here? Yeah, okay. There's a paper from 1998. These are 2 papers about how to try to make cellular automata more like physics. And this one here, crystalline computation, that appeared in a book, Feynman on computation. And it sort of talks about exactly this issue of how to have an interesting world with cellular automata.
Okay.
All right. Anything else?
Sir, I had one more question actually.
Okay.
Sir, I have seen your thesis. I have looked your thesis, physics and computation, where you have told that logically computation is the most energy efficient, and this was the motivation behind considering computational capabilities of reversible logic. I believe that was the motivation for what you started designing this cellular automata machine with Professor Tom Toffoli, and also that may dissipate less heat. So, what was there any advancement required? What is the advancement in that machine that has been taken place in current days? That I wanted to know. Actually.
Okay, let me first of all say that part of that question is a myth. Okay, that Fredkin's motivation and also my motivation and Tom Toffoli's motivation was not actually to make more efficient, energy efficient computers. It's certainly the case that's why lots of people found reversibility interesting, because in principle there's no lower bound on the energy dissipation if you do things reversibly. But all of our motivation was because microscopic physics is reversible, and we wanted to make things that were like physics. Okay, so we weren't actually that concerned about whether the things were energy efficient. There was actually a project at MIT that was exactly that with Tom Knight, and they actually made reversible chips with CMOS. They used the reversibility to be able to never connect two wires together that were at different potentials. And so you don't get this kind of dissipation. It's sort of like opening a box of gas. The particles are all on one side and the other side's a vacuum, and you open the thing in between and you get lots of dissipation as the gas, swirls around and equilibrates. If you avoid that kind of operation, you can make things more efficient. So there was a project, and they even made a chip of this sort that did the billiard ball cellular automaton. Okay, and they made a reversible computer and so on. But it's still, modern computers are still a long ways away from that being the limitation. And there are people like Michael Frank, who's at Sandia, who is working hard on this. I guess we're getting closer to the place where that matters, but that's not the primary. In principle, eventually, if you make your cellular automata models close to physics, then you're going to be able to implement them efficiently with physics. And as we sometimes say, physics is the machine language, right? And then you can get the most efficient computation by programming directly in the machine language. So finding models that are closer to physics ultimately is very important, not just for understanding physics, but for having efficient computation. But I'm more of a theorist, and I'm not building. I want to build cellular automata machines in order to be able to see these interesting universes, not in order to save electricity. The chips I was talking about are designed entirely to try to be able to do very large scale, what I would call bitmap virtual reality. It's virtual, but there was a certain point in time, long before you're aware of, long before you existed, where the displays on computers were not bitmap displays; they were vector displays. You had a CRT, which is this giant tube, and an electron beam, and you drew the thing, right? And you had the displays work that way because each bit cost several dollars, and nobody had enough money to have a bit for every spot on the screen. And now everybody's cell phone has many gigabytes of memory and even more gigabytes of flash RAM and so on. Anyway, we're in an era where we could have bitmaps. When people do graphics these days, they still do vector graphics. They don't have a bit for each spot in the world. they have a line, this is the end of the line and that's the end of the other end of the line. You do some complicated computation in order to find out if it intersects anything, right? But we're now at an era where you could have bitmap virtual reality, and so cellular automata and things like it could become very important for simulating everything. Anyway, that's my viewpoint. I'm not sure if that's insufficient.
Thank you so much, sir.
All right.
So can we take some more questions, or you are getting late? Because there are so many raised hands.
Well, I'm happy to answer more questions at another time or something, or if people want to contact me individually, I'm happy to answer questions. There's also, as I mentioned, the way that the memory tricks, for shifting data and updating data and so on, that makes for good software simulations, as well as the potential for enormously fast hardware simulations of the same models. So if anybody is interested in that, I have a project that I started a long time ago that might be fun for people to work on.
Sure, sir. Sir, what is just the final advice from you for us? Like, we are the young cellular automata enthusiasts. We have a lot of inspiration to take from you. So any kind of advice that you want to give us?
I'm not sure I should be giving people advice, but if people give you positive advice, you should accept it. If people give you negative advice, you should ignore it, because you should know better than anybody whether what you're doing is interesting. One thing I can say is, and this is just general advice about career and so on, is people sometimes worry about, am I doing something that's in the mainstream? Will there be somebody at this university or whatever that will advocate for me to have a job there because I'm doing exactly what they're doing, right? And that's one approach to having a career. But what I've found is that if you work on the thing that is most interesting and that you think is the most important, you'll be in a smaller group, but you'll be competing against less people also. And I think in general, if you're doing something as hard as trying to have an academic career, you better be working on something that's interesting enough. Otherwise, you'll lose your motivation and you won't get anywhere. That's just, and that might be bad advice. Maybe some of the older heads here will tell you that you should do exactly the opposite, and they're probably right. But that's what I did, and it worked out okay for me. Okay.
Okay, and one more thing. Do you think that the Fredkin's view on this universe as a computer, that holds for you also? Universe as a cellular automata that you started with, that if someone mocked him, saying if he was a cheese maker, you would have considered that it is a cheese.
Well, at that time, the idea that there was, people, the attitude in physics was that computers were something that you used if you weren't smart enough to solve the equations. Okay, the idea there was some deep connection between physics and computation. The kinds of ideas that are mainstream today, like holographic principle and black hole entropy. Each Planck area is one bit on the surface of a black hole, and all these things. It's very mainstream now, right? The thing that Fredkin believed, which is that the universe is just a classical cellular automaton, I don't think that's actually right. But I think it could be closer than people think. Maybe there's just an extra time dimension or some complicated thing. Nobody understands how quantum mechanics can be the way it is. And a lot of quantum mechanics is just sort of Fourier analysis, which can be applied to any sort of system. I personally think that the fact that we have a way of figuring out what the universe does next doesn't mean that that's the way the universe does it. When people invented thermodynamics, it was sort of this abstract thing that people didn't understand, what the mechanism was, but they had these differential equations, and but it turns out the universe doesn't sort of use pencil and paper and differential equations. It actually, it has some local simple dynamics and things happen. I don't know what the answer is, but I think it is computation, and it might be much closer to classical computation than people realize. But the thing that I have studied is sort of the most classical aspects of quantum mechanics, sort of the opposite of quantum computation. They want to try to get some extra computation, squeeze some extra computation out of the universe by using the screwiest things that quantum mechanics does. Whereas I'd like to try to start to understand quantum mechanics by looking at the parts of it that are most like classical mechanics, or classical computation, really. And maybe that will give us some clues as to, how is it that the universe does what it does? I don't think it's a classical cellular automaton, but I don't know what it is, and I think it's probably closer to classical computation than people realize. So I'll go that far, okay?
Okay. Thank you, sir. Thank you so much. And I'll take your permission to take the questions from the participants, and maybe I can mail that to you. If you have time, you can get back with your answer.
Sure.
If that is okay with you.
Sure, I'll try.
Okay.
If the questions are interesting enough, maybe we can, just talk about it rather than try to do it by writing. But we'll certainly go ahead and do that. And thank you again for having me in your seminar. It was a good opportunity to talk about these things that, it's sort of another part of my life, which is a while ago, but it's still dear to my heart. And I also got the chance to talk about Ed Fredkin, who was kind of a character out of myth and legend, and it was fun to be his student.
Thank you, sir. Thank you so much. It's nice to hear from you. So many things, so many memories, so many stories. Thanks a lot. Thanks
There are more. Anyway, thank you again. And I'm sure there's another person who's waiting to talk, or do you guys have to go on and do your next thing?
No, this is closing our, today we are closing the session. We should start on the next week again.
Okay. Well, I hope you continue to have a fun seminar. I guess you'll have Toffoli and Wolfram next week.
Yeah, Toffoli is there on the last week. Yeah.
Well, Toffoli is which week?
It's May 20.
Oh, okay.
Next week.
I see. Because I looked at the schedule a while ago, and he was still next
I'm very
week.
sorry to interrupt. It's actually May 18th when Toffoli is going to give us a talk.
Oh, May 18th. Sorry.
Yeah.
That's the Saturday. Sorry, I missed the time.
It's on Saturday, May 18th. Yeah.
So it is. So it is.
Wolfram will give us a talk.
Yeah. So I on the schedule I saw they were both on the same day. So that's still true. Okay. Yeah, Tom was going to listen, but he has a new computer, so I have a feeling that it didn't quite cooperate with him. But yeah, you say this is going to be on the YouTube channel, so you can look at it there.
Yeah.
All right. Well, it would have been nice to let him make a couple of comments, but you'll hear from him next week. He can make his comments then. All right. Well, nice to meet all of you.
Thank you, sir.
And yes, and thank you all again. And I hope to interact with you guys sometime in the future.
Yeah, sure. Please, we'll be very happy.
Okay.
Bye, sir.
Bye-bye.
Okay, so I request everyone to please write your questions and queries to me so that I can compile them and send to Professor Margolus. Maybe he can, if the questions are interesting enough, he might give us a schedule again to meet us. And I'm sorry I can't take all of your questions because it's early morning for him. He promised to give 1 hour. I took already 1.5 hours, so that's why I just skipped the questions. Thanks. See you next week.